Hello, today I will be demonstrating ATCO's Pro 1600 Reflow Oven or Reflow Simulator, depending on the configuration of the system. And in this state it's turned off, the cover is closed. I'm just gonna turn the power key switch on, and it's going to open up the cover and have the tray slide out, the loading tray. And then on the laptop, we're gonna select the Pro 1600 control software, and it's going to load the software up. We're looking basically on the main screen. We have a temperature and time graph. So the temperature is in Celsius, time values are in seconds. We also have some external thermocouples that can be mounted to the side and mounted to the product. Usually one, maybe two thermocouples are used for profile development or thermal testing, but there are 7 of them, so depending on an application, usually for soldering, more than one are being used at any one time. And on the screen, I'm just going to click on the profile tab, log into full access mode, and it allows me to modify the settings of a profile. And in this case, I'll just click on open profile, select the sample profile we have, which will have the pre-filled settings for the temperature and time values. And in this example, we're running a JEDEC standard 20 revision E thermal test. So it's reflow simulation of SMDs, and we have a sample lot mounted, basically placed on a scrap FR4 material. You can use FR4, you can use a composite material like Durastone, which is used for fixturing of circuit boards. And one of those thermocouples that we have mounted is mounted on the surface of a package. That's how the standard is based. It's based on the feedback of the component. And we're just going to check off that thermocouple and click start. Once we click start, we have an audible signal that the cover is going to close, and it comes down, takes the tray with the samples along with it. The thermocouple is resting between the seal, so it's not going to be cut or broken. And at this point, the cycle is automated, so we're going to run the temperature graph we had pre-programmed. And we have the temperature again in Celsius. Red line on the graph represents the internal air temperature, and the blue line is the temperature feedback we have from the external thermocouple that's mounted onto the package surface. The speed of the cover, by the way, is adjustable. So we have 2 needle valves. They're right below the power key switch, and those openings allow adjustment of a individual valve for the opening and closing, and that's how we're able to adjust the speed, make it close down a little slower or faster, depending on how the customer wants it to close down. So as the cycle is running, it's tracking the temperature in real time, the internal temperature within the chamber, and then the temperature on the component. There will always be a delta between those. It depends on the mass of the component, as well as maybe the fixture. And that's with any reflow oven or a reflow simulator. That's the whole profiling process of basically making the adjustments within the system to get a desired profile curve as measured by this blue line and displayed on the graph. one of the features that's useful in profile development is the ability to modify the settings on the fly. So if it's the first time we're running this profile and we wanted to make adjustments, if we see we need a little bit longer time at a certain set point, we can click on the profile tab as the cycle is running, and within the window where we have the temperature set point and then the corresponding time set point, we're able to essentially select it, make a change on the fly, and it's going to follow that new change. So usually this is done the first time that a profile is being developed. We're not quite sure if we're at the desired peak, so we can just extend the time, make it slightly longer than necessary, and then as the cycle is running, we're able to track and see where we are in terms of the feedback temperature of that component, and make the change on the fly so that we're able to optimize the profile in a single pass. With the JEDEC Division E, typically we're looking at the peak temperature of 260. In some cases it's 250 depending on the classification table, but if it's 260, there's a variation for a supplier and the user. A supplier wants to be at 260 or above. A user wants to be below the 260 set point. So based on that, we're able to figure out where we are in terms of our peak set point. But right now we're at approaching 260. And then once the set time is complete, there's a cooling function. In this example, the cooling function is, I believe, a few seconds. The cover at that point will open up, the tray will come out, and the external fans are going to turn on and start cooling the components down. And we're aiming to get to the ambient temperature before running a subsequent cycle. So with this JEDEC 20 standard, we need to repeat the same profile 3 times on the same batch of components. And within the profile window, we have a repeat function. In this case, set to 3. So this profile is going to run 3 times. So it's completely hands-off. Reflow, go through the reflow stage, cool down to ambient as it's cooling down right now. And then once that's complete, it's going to take the board back inside the heating chamber and run the subsequent cycle, second cycle and third cycle. Some of the settings we have in the profile would be that repeat function, and we have a lag time, which is 15 seconds. And usually it's just set to about 15 seconds. It's approximately how long it takes for the cover to close down. And then we start the heating cycle. There's also a nitrogen purge. If nitrogen is connected to the system, it will be checked off, and we can specify how long do we want the nitrogen to flow in minutes. If we wanted to reach a certain oxygen level before running the heating cycle, we can extend the lag time, make it 3, 4, 5 minutes, and it will allow the nitrogen to flow within the chamber to get to a lower oxygen concentration before turning on the heating cycle. Then we have different cooling modes. We have pre-open, which is the most common, and we have closed, and we have an open mode. So pre-open means that during the cooling stage, the cover will crack open a little bit, and the fans, or the fan within the exhaust system, is going to turn on. The seal between the heating chamber and the exhaust will open up, and the blower is going to turn on, pull the hot gas out, pass it through a metal and a carbon-based filter, and then force it through the exhaust port that's at the rear of the oven. And then this section right here would be the main section in terms of the profile. In this example, we have ramp 4, which is a ramp 3 degrees Celsius per second to a set point of 220 Celsius, and we maintain that 220 for 60 seconds. So on the graph, it's represented as a ramp of 3 degrees per second to 220, and then once we reach 220, we stay there for 60 seconds. Once the 60 seconds are complete, we go on to the next stage, which is ramp 5, and that's 3 degrees Celsius per second to the next set point, which is 285 Celsius, and then we maintain that for 65 seconds. And then the cooling time with the built-in exhaust is, in this example, set only to 1 second, usually anywhere from 1 to 150 seconds, depending on how fast you want the product to cool. And then we have the external cooling fans set to 400 seconds. So we're making sure that the product cools down to ambient, as well as the chamber cools down as well. Usually, at a minimum, we want to maintain about a 5-minute cool down cycle before we can run the next batch. So it's running right now. As it's doing that, I'm just going to go over a couple of features. So in terms of the facilities, at the back of the system, there's an exhaust port to which we have a flex hose connected. A flex or a rigid hose is fine. The port at the back, that's a 3-inch OD port, or 75 millimeters. So to that we recommend attaching this flex hose. Again, the exhaust section is the bottom part of the oven, so right here. And in the cooling stage, we have the blowers, where the blower turn on, the seal between the exhaust and the cooling section open up, and it will pull the hot gas out, pass it through filters, and then exhaust it through that rear exhaust port. On the front, if we are using nitrogen, this flow meter will show the flow rate. Usually it's set to 200 CFH. Emergency stop will kill the power to the oven. And then going back to the other side, the power connection is a 5-conductor power cable. So we have 3 phase wires, a neutral and a ground. In this case, we have a portable connection here, but usually it's connected to a safety switch or a disconnect switch, and it has to be hardwired because it's a 50 amp draw on this unit, 50 amp max. Usually it's about 45 amps. And the yellow hose is the air connection, so it's a compressed air line. The air is only used for the opening and the closing of the lid, so it's very low volume, low flow. So now the first cycle has completed. The 400 seconds are done, and then the cover closes to start the second cycle and takes the board along with it. So the graph, I'm just going to change the scale. If I highlight that 600 second field, reduce that, this way we're able to see the initial profile and then the subsequent profile that's coming along with it. Some other connections, the communication between the oven and the laptop is via USB port, so it's one USB cable here. Then we have that jack for the cooling fans, the on-off switch, and then right below that, the two openings are for the needle valves to adjust the speed of the cover to open and close. And then we have the 7 thermocouple ports. So on this configuration, the external thermocouples are included, the fans are included as well, and that's part of the Pro 1600 RS. It can also be added to the Pro 1600 EXN version, but for the JEDEC 20 standard, the fans and the external thermocouple are essentially required to be within the process window and to be able to have the feedback of the package temperature as we're running right now. If we were soldering a circuit board or running a production, we would still want to have the multiple thermocouples where you're able to develop a profile based on the feedback of the board, based on the mass of the board and the type of solder paste that's being used. And once the profile is developed, it's saved. There's no need to reattach the thermocouple when running that production lot or batch. For the JEDEC test, you want to reattach the thermocouple if you wanted to have the documentation to show here's the profile and this is how it looks based on the feedback on the package surface. It's not necessary unless, again, it's for showing it to a customer or internal documentation purposes. Footprint is 31 by 31 inches. One of the options is the laptop stand that we have. The laptop is included in the EXN or the Pro 1600 RS models, and some customers place the oven next to a workbench, so the laptop stand may take up additional space that they don't need to take up. That's why it's optional. Again, it's not necessary. The laptop is included. Software comes pre-installed, and the system is calibrated when it ships. So now we're finishing up the reflow stage of the second profile, and then we have the cover open up, the tray is sliding out, and again, just like with the first cycle, the parts are cooling down to ambient temperature before running the profile again, running it for the third time. In terms of the parts and the fixture, this is a scrap FR4 board, and we have Kapton tape. The parts are very small. We can place Kapton tape and place the parts on top of that. This way they don't move or slide. There's not case of excessive vibration, but since there's no solder paste or flux, they can slightly shift. The Kapton tape keeps them in place. Other options are to use a composite material as a fixture. Durastone is very popular. It's used for circuit board fixturing. It doesn't act as a heat sink, so it's very durable, withstands the temperatures, and doesn't suck the heat away from the component. And we have the thermocouple mounted to one of those components, one of those ICs. Usually we're just using Kapton tape, copper or aluminum tape to hold the thermocouple in place, and then Kapton tape over that just to make sure it doesn't pop off. So we are looking at that graph again. In terms of the board, you can basically put it down. Doesn't matter where which position on the loading tray. The size of the tray is 20 by 20 inches or 500 millimeters squared. So we can fill this whole loading tray up. The main point is to make sure that the components are separated from one another. They're not making contact. This way, in terms of the thermal mass, they're individual, but the system has enough capacity to run either a small lot of 20 or 30 components to basically a large lot that will fill this whole tray. The profile will be the same. It's not going to differ whether you have 10, 20, or again, have the whole tray filled up with these components. So it's cooling down. In terms of maintenance, there's no routine maintenance outside of periodically backing up the profiles. Any new profiles that are added on, we recommend periodically backing them up to a network drive or a flash drive. The software comes as a backup, but if the laptop has to be replaced, any new profile that was developed from after the system has been delivered would not be there, so you want to make sure that there's a backup of that. Also, if the system is used for soldering, the interior is all stainless steel. Over time there might be flux residue that's going to build up, so we just recommend using isopropyl alcohol as a solvent to wipe the stainless steel chamber and remove any excessive flux buildup. It's normal to have flux buildup, but to a degree. In this case, the JEDEC testing, the reflow simulation, we're not using solder paste, we're not using flux, so there's no residue to be concerned about. So while that's running, we can take a look at the profile. Usually in terms of profile development, we have some sample profiles, or a customer has some profiles that they use often. With a new part, new component that they're running, they're able to typically just pull up an existing profile and make some slight adjustments to it. So you don't necessarily have to start completely from scratch. Taking an existing profile and making some slight modifications is usually the process in terms of creating a new profile. So we would, if we're running components that are slightly larger than what we currently have, we would take this profile and, as an example, I would probably just leave the temperature values the same as they are right now. The main setting I would play around with would be the time at a temperature. So the 60 seconds, I can make it 100 seconds for T4, and the 65 seconds, I'll increase that as well. And as we're running the profile, we'll get the feedback of the component. If we see that we're not quite at the desired temperature as we're approaching it, we can go into this window again, make that modification on the fly, and we're able to tailor that profile in a single pass. So the 400 seconds of cooling are complete, and again the cover is closing, taking the tray with it, and it's going to run the profile again, that third cycle. So as the cycle is running, there's no user input at this point. It's again, it's all automated. Some of the icons on the main screen, the start icon, since it's running, is grayed out, so we can't modify that. Once the cycle stops, it will be solid green again. Then we have a cycles left field that shows how many cycles we have left in this profile. Nitrogen is currently off. If we had nitrogen purge, it will show the time remaining of that nitrogen purge, as well as if for some reason necessary, we can toggle that nitrogen on and off. The stop icon will terminate the cycle. The difference here is that e-stop will just turn off power to the oven. We'll have a power is off message come up on the screen. The stop would be if the operator forgets to apply solder paste to a certain part or add any additional flux. They can just hit stop to terminate the initial cycle. Save data would be raw data if we wanted to capture that raw data file, the temperature and the time of this profile. And it's a text file. We can send it into Excel if we wanted for additional documentation or resolution. That's there. But usually we would just do a print screen of this graph. We can again modify the scale. So if I wanted to reduce this back down, I'm gonna scroll through each profile. I can do that to get a better resolution and determine time, temperature, parameters like that. It's running. Again, we can see the peak temperature on the external TC1. That's the temperature on the surface of the component. Again, fans turned on, the cover is opening up. So we can see in terms of the peak, it's hitting the same 260 set point. Each of these profiles, a certain repetition and consistency. Back down. So we're able to see all three graphs. I click on the calibration tab. Calibration is something that the end user can do. It's outlined in the manual, and basically we have an internal sensor within the heating chamber that's controlling the cycle. We have the offset, which is this calibration. The offset is the temperature that's being measured at the loading tray is slightly different. Hence, we have a calibration offset value. So we take a thermocouple from a known good calibrated meter, we mount it on the work area, which is a loading tray, and we're on the calibration profile. At peak temperature set point, we're taking the reading of that meter and we're putting the value in where it says thermometer reading and click calibrate. So what it's doing is just taking an offset of the temperature that the internal sensor is reading within the heating chamber relative to the temperature that the external thermocouple of the meter is reading, and that's our calibration procedure. So it's a quick, very straightforward process, and when we do program that temperature value of 220 or 285, it corresponds to the actual temperature at the work area, at the surface where the components are being placed or the circuit board is being placed. Some of the other options we have for the system would be a double-sided board fixture. It's not installed on this unit, but basically for soldering circuit boards, and they have components on top and bottom side. Initially placing the circuit board directly on the loading tray, you can run the reflow, but then the board has to be flipped upside down for the second pass. And so that fixture is essentially just mounts right over this mesh loading tray and allows the board to be secured along opposite edges. Again, useful if you're doing reflow of double-sided boards, but would not be necessary for reflow simulation that we just did right now. Another option that we have would be, in addition to the 7 thermocouples we have mounted on the side, there's an external thermocouple control option. What that allows us to do would be to take this thermocouple and run it in a closed loop process. So we can attach a thermocouple, usually for prototype types of soldering of circuit boards, mount the thermocouple to a prototype board, and then in the profile window, instead of making the adjustments of air to board temperature adjustments that we did with this profile, or is done in any traditional reflow oven and reflow soldering application, we would change the control mode from internal thermocouple to this external TC. So in this example, it would run based on the feedback temperature it's reading at the circuit board, and the profile settings would be the settings we want the board to be subjected to. So the temperature inside the chamber will automatically adjust based on that feedback that it's getting from the circuit board. So we're running in a closed loop process. It's not recommended for traditional production kind of reflow because it will require attaching a thermocouple every single time. Plus the resolution is much better and it's a lot more consistent if we're running the traditional profile as we're doing right now, not basing on an operator attaching a thermocouple and where they're attaching. So it's a useful external thermocouple control, a useful option if you intend on running some prototypes, low volume builds where you don't want to spend the time doing the traditional profiling process, and just place a board in, attach a thermocouple, and it's going to be within the process window. But for a traditional kind of reflow, you want to create a profile based on the internal thermocouple control. So it's almost complete. Process finish, the start icon is solid green, so we can run the next batch, take this batch off, and basically just remove it, and then place the next batch. Before we do that, we can click on Save Data and title it Data. So we have the raw file saved up. Go to Profiles, and this is the file that was just generated. Has the profile settings that we have, and as well as all the raw data for the external thermocouple, internal thermocouple, and the time value. So this can be sent into Excel if necessary for further analysis, but most of the time we would just do a print screen. Go to Paint and just dump that image in there, and then save it for documentation purposes. We can also, again, reduce the scale here. So if we wanted to see each individual profile at a higher zoom, we can do that as well. And then in terms of the profile, if we did make any of the changes as we were running it, or if it's a profile that we pulled from before on a new batch and made the adjustments for this specific component, we can click on Save Profile, title it whatever we want, click OK, and then save it. So technically anytime we want to run this profile again, there's no need for the adjustments. We're just pulling up an existing profile from memory and just running based on those settings. So that's basically it for the system. If there are any questions, feel free to reach out to me, give me a call, or send me an email. Thank you.